Let me tell you something that should bother you a lot more than it does. Drop a rock, watch it fall. You've done this since you were 2 years old. You understood it before you understood language. And I am here to tell you that nobody, not me, not Einstein, not a single living physicist actually knows what is happening when that rock falls. We know how to predict it. We've known how to predict it since Newton, and we've known how to predict it more precisely since Einstein. But predicting and understanding are not the same thing. And the gap between those two words is where I have spent the better part of 50 years, and it is where I am going to take you tonight. Whether you came here for that or not, here's what you think you know about gravity. You think it's a force like the others. You learned that in school there's electromagnetism, there's the strong force, there's the weak force, and there's gravity, four forces, all basically the same kind of thing, just with different strengths and different jobs. Electromagnetism holds atoms together. The strong force holds nuclei together. The weak force lets nuclei decay, and gravity holds planets and stars and galaxies together. Four siblings in the same family. That's the picture you walked in here with, and I am going to spend the next several thousand words taking that picture apart, because it is wrong, and the way it's wrong is the most interesting fact in physics. Gravity is not like the other forces. Gravity is not a force at all, not in the way the other three are forces. This isn't me being cute or poetic. Einstein figured this out in 1915, and I want you to feel the weight of what he actually did, because it gets glossed over in every popular account I have ever read, and it is the single most important intellectual move in the history of physics. Einstein said, "Gravity is not a force pushing or pulling objects through space. Gravity is the shape of space itself. Mass and energy bend the fabric of space-time, and objects moving through that bent fabric simply travel the straightest path available to them, and that straightest path looks to us like falling." Sit with that, because I promise you, most people who say they understand general relativity have never actually sat with it. When you drop that rock, the rock is not being pulled by anything. The rock is doing exactly what a rock should do if left completely alone, moving in a straight line through space-time. It is the Earth's mass that has warped space-time around it so severely that straight now curves downward toward the ground. The rock isn't falling because something is grabbing it. The rock is falling because the geometry of the universe has changed shape beneath it, and a straight line in that new geometry happens to end at your foot. I remember the day this actually clicked for me. Not when I first learned the equations. Anyone can learn the equations. That's just bookkeeping. But the day I understood it in my gut. I was a young guy, brash, full of opinions. The kind of physicist who annoyed his professors by asking, "But what is actually happening?" instead of just solving the homework. And one of my teachers, exhausted with me, finally said, "Stop asking what's happening and start asking what's invariant. What stays the same no matter who's watching, no matter how they're moving." That single redirection changed how I do physics for the rest of my life. Because here's the move Einstein made that nobody tells you about in high school. He didn't start with gravity. He started with the question of who gets to say what straight means and who gets to say what time it is. And once he figured out that different observers moving at different speeds disagree about distances and disagree about durations, but agree on something deeper, a combined quantity called the space-time interval, gravity fell out of the math almost as a side effect. He wasn't hunting gravity. He found it by asking a more basic question about the nature of measurement itself. Now, here's where it gets strange. If gravity is geometry, if it's the shape of space-time, then gravity isn't really a thing sitting inside the universe the way an electron is a thing sitting inside the universe. Gravity is the stage, not an actor on the stage. And this creates a problem so deep that it has eaten entire careers, mine very much included, because every other force we know, electromagnetism, the strong force, the weak force, gets described by quantum mechanics. Quantum mechanics is the operating system of reality at small scales. It says particles don't have definite positions and momenta simultaneously. It says outcomes are probabilistic until measured. It says fields are made of discrete quantized packets, photons for light, gluons for the strong force, and so on. We have built quantum descriptions of 3 of the 4 forces, and they work to absurd precision. The magnetic moment of the electron, predicted by quantum electrodynamics, matches experiment to about 10 decimal places. 10 decimal places, that is not an approximation. That is one of the most spectacular agreements between theory and experiment in the history of science. And gravity has resisted quantization for over a century. And I want to be honest with you about why, because the popular explanation, it's just really hard math, is true, but also completely misses the actual philosophical wound. The wound is this: quantum mechanics needs a fixed background of space and time to operate in. When you write down the quantum theory of an electron, you write down its wave function evolving through space as a function of time. Space and time are the stage on which quantum mechanics performs. But general relativity says space and time are not a fixed stage. They are dynamical, they bend and warp and ripple depending on what mass and energy are doing. So if you try to quantize gravity the naive way, treat the metric of space-time itself as a quantum field, the way you'd treat the electromagnetic field, you are trying to quantize the very stage that quantum mechanics requires to make sense of anything. You are asking the floor to wobble while you're trying to use the floor to measure how things wobble. This is not a technical inconvenience. This is a conceptual knot at the foundation of physics, and we have not cleanly untied it. Anyone who tells you we have is selling you something. Let me give you the thought experiment that makes this concrete, because I don't want this to stay abstract. Abstraction is how people fool themselves in this field, mine included. Imagine you have a single electron, and you want to know quantum mechanically where it is. Quantum mechanics tells you it doesn't have one location, it has a probability cloud, a superposition of being in many places at once until you measure it. Fine. Bizarre, but we've tested this 1,000 ways and it holds up. Now here's the question that should keep you up at night. If that electron has mass and mass curves spacetime, then what does spacetime look like around an electron that is simultaneously here and there in superposition? Does spacetime itself split into a superposition bent one way around the here branch, bent another way around the there branch? Or does gravity somehow force the electron to choose a location before quantum mechanics would otherwise make it choose? Nobody knows. I mean, that literally there is no experiment that has ever probed this regime, because gravity is so unbelievably weak compared to the other forces that we cannot test quantum gravitational effects on anything as light as an electron with any technology we currently have or are likely to have soon. This is not a settled question with a textbook answer. I'm simplifying for you. This is an open wound. And I want to pause here and tell you something that took me decades to fully appreciate, because it connects to a fight I actually had in public with one of the smartest men who ever lived. And I do not say that lightly. In the 1970s, Stephen Hawking made a discovery that should have been the end of a long and productive friendship, and instead nearly ended several careers, mine included. In a slower, more painful way, Hawking showed that black holes are not the perfectly silent, perfectly absorbing objects everyone assumed. Combine quantum mechanics with the curved spacetime near a black hole's horizon, and the black hole emits radiation. It glows, faintly, but it glows, and over an unimaginably long time, it evaporates entirely. This is one of the most beautiful results in theoretical physics, Hawking radiation, because it's the first real working bridge between quantum mechanics and gravity that produces a concrete, calculable prediction. People should be in awe of it. I am still. But Hawking didn't stop at black holes' glow. He pushed further and said something that, if true, would have broken quantum mechanics itself. He said, when a black hole forms, information about everything that fell into it, every particle's exact quantum state, every detail gets fundamentally destroyed, not hidden, not scrambled and recoverable in principle, actually permanently erased from the universe, lost when the black hole finally evaporates into nothing but featureless radiation. And quantum mechanics has a sacred rule baked in from the very beginning called unitarity, which says information is never truly destroyed. It might get scrambled beyond any practical hope of reading it, but it is never erased from existence. Hawking was telling the world that black holes break this rule, that gravity, in its full quantum glory, defeats quantum mechanics' own deepest principle. I thought he was wrong. Not I had a hunch. I thought he was making an error, and I spent close to 30 years trying to prove it. And I will tell you honestly, there were stretches of years where I was not at all sure I would win this argument, and some sleepless nights where I suspected Hawking might simply be right and the rest of us were the ones not facing reality. That's the part nobody puts in the textbook summary. Real physics doesn't feel like calm confidence. It feels like genuine uncertainty about whether your whole framework is about to collapse. What finally broke the deadlock, and this is where the topic of tonight's talk and the topic of that decades-long war actually fused together, was a deeper question about what space and information actually are. A piece of work building off ideas from Hooft and developed properly into what's called the holographic principle, suggested something which still sounds, frankly, insane when I say it out loud, and I've been saying it out loud for 30 years. The holographic principle says that all the information contained inside some region of three-dimensional space can be fully encoded on the two-dimensional boundary of that region, like the universe is. In some deep mathematical sense, a hologram, where the three-dimensional world we experience is a kind of projection of information actually living on a lower dimensional surface. This was not poetry. This came out of very careful calculations about how much information a black hole can possibly contain, tied to the area of its event horizon rather than its volume, which is itself a strange and important clue. Because normally, if you want to know how much stuff or information fits in a region, you'd think about its volume, not the area of its surface. Black holes broke that intuition first, and the holographic principle took the break seriously instead of explaining it away. Now, here's where it gets strange again, because in this field, it keeps getting strange. That's the whole nature of the territory. If information about everything that falls into a black hole is encoded on its horizon, then the information isn't destroyed when the black hole evaporates. It's radiated back out, scrambled almost beyond recognition, encoded in correlations across the Hawking radiation in a way so complex it would take longer than the age of the universe to decode with any realistic method, but not actually erased. Unitarity survives. Quantum mechanics wins. And Hawking, to his enormous credit, and I want to say this plainly because it matters eventually, conceded, he didn't dig in out of pride. He paid up on a bet, literally, an encyclopedia, and more importantly, he changed his public position. That is what intellectual honesty looks like at the highest level of this profession. And if you remember nothing else from tonight, remember that the goal was never to be right. The goal was to find out what's true. And sometimes that means losing an argument you spent years defending. And here is the humility I promised you. Here is the part that is not comforting. Winning that specific battle did not mean we solved quantum gravity. It meant we found a strong piece of evidence from a very particular and somewhat artificial corner of the theory that quantum mechanics and gravity are not as incompatible as they first appeared, at least in certain idealized situations. The actual mechanism, how in physical detail information gets out of a black hole, what the actual microscopic moment by moment physics looks like, that is still being worked out today in 2026 by people younger than me, using mathematical tools that didn't exist when I was developing these ideas. We have strong indirect evidence for an answer. We do not have the answer written out in full. Anyone who tells you otherwise has confused "we found a convincing argument" with "we found the mechanism," and those are not the same achievement. Let me back up, because I've taken you pretty far down one tunnel, and I want to show you the broader landscape. Because the black hole information story is dramatic, but it is not the only road into this mystery. And it would be intellectually dishonest of me to make it sound like the only road. The deeper approach, the one I've spent most of my working life on, is string theory. And I want to tell you honestly what string theory is and is not, because It has been wildly oversold by some people in my field and wildly underestimated by others, and the truth sits, as it usually does, somewhere uncomfortable in between. String theory starts from a simple, almost embarrassingly simple proposal. What if the fundamental constituents of reality are not point particles, zero-dimensional dots with no internal structure, but tiny, one-dimensional vibrating strings? A string can vibrate in different modes, the way a guitar string can play different notes, and the proposal is that each vibrational mode corresponds to a different particle. One mode gives you an electron, another gives you a photon, and this is the part that made people's hair stand up when it was first noticed in the early 1970s. One particular vibrational mode, completely unforced, completely unavoidable, if you do the math honestly, has exactly the properties physicists had already calculated a hypothetical particle called the graviton would need to have. The graviton is the particle that would carry the force of gravity, the way the photon carries electromagnetism. String theory wasn't built to produce gravity. It stumbled into gravity, uninvited, and that is one of the most remarkable accidents in the history of science. You set out to describe the strong force using strings in a model that initially had real problems. And tucked inside the wreckage was a particle behaving exactly like gravity should behave at the quantum level. Nobody planned that. It just fell out of the math. And when something falls out of math that nobody asked for, and it happens to be the thing everyone was desperately looking for, you pay very close attention. I want to give you a second thought experiment here, because gravitons deserve one. Imagine two electrons far apart interacting electromagnetically. In quantum electrodynamics, we say they're exchanging virtual photons, tiny packets of the electromagnetic field flickering between them, and that exchange is what we experience macroscopically as the electric force. Now, imagine the same two electrons, but instead think about their gravitational attraction. Yes, electrons have mass, so they attract each other gravitationally too, even though the effect is so laughably weak compared to their electric repulsion that for two electrons, it's never going to be the dominant effect. But in principle, in the quantum picture, that gravitational attraction would be mediated by an exchange of gravitons, the same way electromagnetism is mediated by photons. String theory's claim is that if you build your particles out of vibrating strings instead of points, the graviton you need for this picture comes out automatically, consistently, without the mathematical sicknesses, the infinities, the nonsensical predictions that plague every attempt to quantize gravity using point particles directly. That consistency is not nothing. It is, in fact, the main reason serious people have spent 50 years on this theory, despite the brutal difficulty of testing it. And here is where I have to be honest with you in a way that some of my colleagues find uncomfortable, because honesty sometimes costs you allies. String theory to this day has not been experimentally confirmed. I am not going to stand on a stage and pretend otherwise to you, because I spent my whole career arguing against exactly that kind of dishonesty when other people did it about other ideas. The energies required to directly probe strings to see their string-like nature rather than their effective particle-like behavior at low energy are so far beyond what any particle accelerator on Earth, or plausibly imaginable on Earth, could ever reach. That direct detection, in the way we detected the Higgs boson, is not currently on the table. What we have instead is a rich mathematical structure that is internally consistent in places where every previous attempt at quantizing gravity broke down, that reproduces general relativity in the right limit, that predicts gravity must exist rather than assuming it, and that connects unexpectedly to other areas of physics, including, as I mentioned, that holographic business with black holes, where string theory and the holographic principle turned out to be two views of the very same underlying mathematics, something called the ADS-CFT correspondence, worked out properly by Juan Maldacena in 1997, which to this day I consider one of the most important results in theoretical physics produced in my lifetime, even though most of the general public has never heard of it because it doesn't reduce to a sentence you can put on a coffee mug. You're probably thinking right now, if string theory hasn't been tested, why should I believe any of this rather than treat it as elaborate mathematical fan fiction? That's a fair question, and I want to actually answer it rather than wave it away, because waving away fair questions is exactly the kind of intellectual cowardice I have spent my life despising in other people. The honest answer is you shouldn't believe string theory the way you believe quantum electrodynamics, which has that 10 decimal place confirmation I mentioned earlier. You should hold it the way a careful person holds a strong hypothesis worth pursuing because of its internal consistency and its uncanny tendency to produce gravity and other known physics without being asked to, but not worth treating as settled fact, because settled facts in physics come from experiments, not from elegance. No matter how badly we want elegance to be the same thing as truth, I have watched good physicists fall in love with beautiful equations and forget this distinction, and I include younger versions of myself in that accusation. Now, there is another major approach to this problem, and I'd be doing you a disservice and frankly insulting an entire community of serious physicists if I pretended string theory was the only game in town, because it isn't, and the disagreement between these approaches is itself one of the more interesting fights happening in physics right now. Loop quantum gravity takes a different starting assumption. Instead of asking what are the fundamental particles, it asks what is space itself made of, and answers. Maybe space is not smooth and continuous the way it appears to us, but is instead built from discrete, quantized chunks at the smallest possible scale, something called the Planck length, about 10 to the minus 35 meters, a length so absurdly small that if an atom were scaled up to the size of the observable universe, the Planck length would still be smaller than that atom was originally. Loop quantum gravity tries to quantize space-time geometry directly, treating area and volume themselves as having discrete, countable values, the way energy levels in an atom are discrete rather than continuous. It has had real successes. It produces sensible, finite answers for the area of a black hole's horizon in terms of countable quantum units, which connects right back to that information puzzle I described earlier. But it has struggled, more than string theory has, to naturally reproduce ordinary particle physics. The electrons and quarks and photons we already know exist within the same framework, and that is a real weakness, not a minor one. I bring this up because I want you to understand this is a live, contested, unresolved scientific argument among serious people, not a solved problem, where one camp is obviously and uncontroversially correct, and I'm just being modest. If someone tells you physicists have figured out quantum gravity, ask them which version and watch them either pick a side they can't fully defend or admit the truth, which is that we don't know yet. Here's what's really going on underneath both of these approaches, and underneath every serious attempt at this problem for the last 100 years. And I think this is the part that actually matters most, more than which specific theory wins. The deep mystery of gravity is not really a mystery about gravity. It's a mystery about the nature of space, time, and information, and gravity is simply the place where that mystery becomes impossible to ignore. Every other force operates within space and time as guests in someone else's house. Gravity is the house. So when you ask, how do we quantize gravity, you're secretly asking, what is space and time made of, fundamentally, if not the smooth, continuous backdrop Newton and even Einstein assumed it to be? And that question reaches further than physics typically likes to admit out loud. It touches questions about whether space and time are fundamental at all, or whether they are themselves emergent, built up out of something more basic, the way temperature emerges from the statistical behavior of countless individual molecules, even though no single molecule has a temperature of its own. That idea that space-time itself might be emergent, might arise from the entanglement structure of some more fundamental quantum system, the way a hologram emerges from interference patterns on a flat photographic plate is not science fiction. It is an active, serious research program, and some of the strongest evidence for it comes directly out of that ADS CFT correspondence I mentioned, where an entire gravitating universe with curved space-time turns out to be mathematically identical, dual, to a completely different theory, living on its boundary that has no gravity in it at all. Space-time, in that very precise mathematical setup, is not fundamental. It's built, and once you've seen that happen in one rigorous controlled example, you cannot unsee the possibility that it happens generally, including possibly in the universe we actually live in. Let me bring this down to Earth for a second, because I've been flying pretty high and I don't want to lose you up there. Why should you, a person who is not a theoretical physicist, who has a job and a family and bills and absolutely no professional need to care whether space-time is emergent, actually care about any of this? I'll tell you why, and it's not a sentimental answer, it's a practical one. Every technology you use that depends on quantum mechanics, and that's most of modern technology. Your phone, the GPS satellite that knows where you are, every semiconductor in every device around you exists because people took quantum weirdness seriously instead of dismissing it as philosophical nonsense. The transistor came out of people willing to sit with the discomfort of quantum mechanics long enough to actually use it. Right now, today, gravity is the one place in physics where we are still sitting in that same discomfort, unresolved, and I genuinely do not know what comes out the other side of resolving it. Maybe nothing practical for 100 years, maybe nothing practical ever, if it turns out the relevant physics is locked away at energies we will never reach. Or maybe, and history gives us real reason to take this seriously, because nobody in 1905 had any idea that special relativity would end up mattering for the clocks on GPS satellites, which have to correct for relativistic time dilation or they'd be useless within a day. Maybe understanding quantum gravity properly reveals something about the structure of information and computation and reality that changes what's technologically possible in ways none of us can currently picture. I'm not promising you that. I'm telling you the history of physics has a pattern. And the pattern is that foundational questions, which look completely useless, turn out decades later not to be useless at all. And the people who dismiss them as useless usually end up looking foolish in retrospect. That's just wrong, by the way, the idea you sometimes hear that this kind of foundational physics is a luxury, an indulgence, disconnected from anything that matters. I've heard that argument my whole career, usually from people who haven't sat with the actual mathematics long enough to see where it leads. The people who discovered quantum mechanics in the 1920s were not trying to build a smartphone. They were trying to understand why atoms don't collapse, a question that seemed almost embarrassingly abstract at the time. Don't let anyone tell you the abstract and the practical are cleanly separable in physics. They never have been, not once, not in 400 years of doing this seriously. I want to give you one more thing before I bring this to a close, and it's the part of tonight's talk that I think is actually the most honest, because it's the part where I tell you what I don't know rather than performing confidence I don't have. There is a deep tension, still completely unresolved, between the picture of gravity as smooth, continuous geometry, which is what general relativity gives us, and which has been tested to extraordinary precision, including the direct detection of gravitational waves starting in 2015, ripples in space-time itself, exactly as Einstein's equations predicted a century earlier. A result so beautiful, it genuinely brought tears to the eyes of grown physicists who had spent their careers waiting for it. And the picture of reality is fundamentally discrete and probabilistic at the quantum level. These two pictures have never been fully reconciled into one single coherent framework that everyone agrees on. And that has been experimentally confirmed the way quantum electrodynamics has been confirmed. We have strong partial results. We have beautiful mathematical dualities. We have one specific dramatic battle, the black hole information war, that I believe we won, with the emphasis on believe, because even that victory rests on theoretical arguments rather than a direct experimental measurement of information escaping an evaporating black hole, which is an experiment nobody alive will ever perform, because the black holes we can actually observe are not even close to finished evaporating. That process for an astrophysical black hole takes a span of time so much longer than the current age of the universe that the number is almost an insult to write down. What keeps me up at night, even now, even after everything I just told you, is not whether string theory or loop quantum gravity or some idea nobody has thought of yet turns out to be correct. What keeps me up at night is a more basic worry that we might be asking the question in a fundamentally wrong way. The way physicists before Einstein were asking entirely reasonable, careful questions about the ether that light was supposed to be vibrating through, right up until someone realized the question itself was malformed, that there was no ether, and the whole apparatus of the question needed to be thrown out rather than refined. I do not know, and I want to be completely honest with you that I do not know, whether quantum gravity is a problem we are close to solving with smarter math applied to the same basic concepts, or whether it's a problem that requires throwing out some assumptions so basic that none of us, including me, with 50 years invested in this, have even identified it as an assumption yet. That uncertainty is not comfortable. It is not the kind of thing you put in a textbook with a confident summary box, but it is the actual honest state of this field, and I would rather give you that honest discomfort than a tidy lie. So here is where I leave you, and I want you to actually sit with this on the way home rather than just nodding and moving on with your evening, because that would defeat the entire purpose of standing up here and saying all of this out loud. Gravity is the only one of the four forces we have never successfully folded into the quantum picture that governs everything else in this universe. Every atom in your body, every photon hitting your eye right now, every transistor switching in the phone in your pocket. And the closer we look at why gravity resists that folding, the more it looks like gravity isn't really a force that happens to be hard to quantize. It looks like gravity is the shadow cast onto our limited human perspective of some deeper structure involving information and entanglement and geometry that we've only glimpsed in narrow, idealized mathematical corners, a black hole here, a holographic duality there, and have not yet seen whole. We have won real battles in this war. The information paradox, I believe, is settled, or close enough to settled, that I will stake what's left of my reputation on it. But the war itself, the project of actually understanding what space and time and gravity fundamentally are, rather than merely predicting how they behave, that war is not over, and I will not stand up here and tell you it is, because every physicist who has ever told you a war like that was over has eventually had to eat those words, sometimes publicly, sometimes with an encyclopedia changing hands as proof. The rock is still falling. We can predict exactly where it will land, to as many decimal places as you like. We still do not fully know why there is a where for it to fall toward in the first place, or what it really means that mass tells space how to bend and bent space tells mass how to move. Go home, and the next time something falls in front of you, I want you to actually feel uneasy about it for a second, the way I still do every single time after 50 years of this. That unease is not a failure to understand physics. That unease right now, today, is the most honest and accurate understanding of gravity that the human species has